There are 5 sp3d hybrid orbitals that we're using to do the bonding here, but the way we phrase it is we would say that the hybridization of the central atom is simply sp3d. But you're right, there are 5 orbitals, and that's a really important concept. Okay, good question, Caitlin. Okay, so here's my sp3d hybridization. What is the geometric name that's associated with this hybridization? Trigonal, bipyramidal, bipyramidal. I don't care how you say it as long as you can recognize it. So it's got 2 axial positions. Remember, axis like a globe? Yeah. Okay. It's got 2 axial positions and then 3 equatorial positions. You can see I can spin it around like a globe. Okay, so that's our trigonal bipyramidal. What are the bond angles in here?
120, 90, 180.
120 from outer to inner to outer. What else?
90.
90 from axial down to equatorial. And what else?
180.
180, exactly. Very good. Okay. All right, let's do pH 3. Same set of answer options. Go. As you come in, go ahead and click these out so you can throw an answer in there for me real quick. Thanks for being here.
Where's 2?
किसका करना है? PH3
PH3
SP3
So that's I just said it a minute ago, but what's the geometric name that correlates to sp3 hybridization? Tetrahedral. Now, remember, show me what tetrahedral is not. There you go. It's not 90-degree angles. Okay, now, is the shape... I saw that. You did tetrahedral. That made my day. So... what is did anybody go Google Mary Catherine Gallagher? Anybody go Google that? Go Google Mary Catherine Gallagher Superstar. It will amuse you. Okay, is the shape of pH3 tetrahedral? No. Why? Because it does in fact have that lone pair, and my nifty model kit has little lone pairs here. So now we end up with this guy. Okay? So notice that what's the shape that you can see right here? Triangle, trigonal, but it's not flat. See if you see how it's not flat? You see that space between my hand and the atom? So it's a little pyramid. It's not planar, not trigonal planar, it's trigonal pyramidal. See the difference? Trigonal planar would be all in, the same plane, and would look like, give me just a second here, and would look like that. See how it's flat? Okay, so you see the difference between them? Okay, so be really careful with that. Okay, let's not do a clicker for this last one here, but what is the hybridization? I drew it for you last time. What's the hybridization for the central atom here? sp2, very good. And the geometric name and shape both are trigonal planar because there's no lone pairs on the central atom, right? On the central atom. Okay? We did a little bit more with geometric name and shape. I'm not going to make them clicker questions, but I do want to get you answers for these. What'd you come up with for SF4? What's the geometric name for SF4? Trigonal bipyramidal, good. Now how did you get 5 regions if there's only 4 atoms? Lone pair on central atom, excellent, excellent. So what we have is something that looks like this. And I drew it this way for a specific reason. What's that shape?
Seesaw.
It is in fact a seesaw. The reason it's seesaw is because the lone pair must go in the equatorial position. It cannot go in the axial position. When you put it in the axial position, you create a whole bunch of small angle repulsions between the lone pair and the bonding pairs. You would in fact make 3 90-degree angle repulsions, right? And we want to minimize those repulsions. By putting it into an equatorial position, I only have 1, 2 90-degree angle repulsions, and my others are 120. So that's a better arrangement to minimize the repulsion. And we end up with our seesaw, right? See what I mean? Okay, so that's a seesaw shape. Excellent. Did you have a question? No, sorry, you were discussion. All right, one more, BRF5. What do we have for BRF5? What do we end up with? How many, what's the electron, what's the geometric name? It is octahedral. It does have 6 groups around it because, again, we've got a lone pair. So we've got BR, we've got a lone pair. That's a really ugly lone pair, but we're going to go with it. So we end up with octahedral electron group arrangement, but what is the shape? What's it called? Square pyramidal. Square pyramidal. Square pyramidal. Yes, absolutely. So let's take a look. Now, does it matter where I put the lone pair in an octahedral molecule? No? Yes. No.
No.
No, yes.
No.
No.
It's not matter.
Raise your hand if you think it matters. Everybody has to vote. Okay? I like this. See, we're proud over here of our vote. Thank you. Confidence. I like it. Who thinks it doesn't matter? Who will confess that they didn't vote? There we go. I like that. Thank you for honesty in the back row. Okay? So here is our, I know these are a little hard to see, but I hope it's a little bit better than 2 dimensions. This is octahedral, right? This is an octahedral geometric name because I have all bonding pairs, correct? Okay. Axial. Where we see axial? Right? Axial. Or is it equatorial?
Good question.
Axial. Equatorial. Axial. Equatorial. What are the bond angles here? 90. And? 180. Okay. No 120s, right? So is there in fact a difference between an axial position and an equatorial position? Only depends on, only from the perspective of which way are we looking at it, right? So the first lone pair I can put wherever I want. What shape are you seeing here? It's a square, but it's not flat, right? So it's square pyramidal. Okay. Where's the second lone pair have to go? Does it matter where the second lone pair goes? Do I want to put another lone pair here? No, that's a 90-degree angle. That's the smallest angle we can have in a molecule. Well, from the ones we've looked at. That's the smallest angle we've looked at with 2 lone pairs smashed into that small angle. No way, no how. That is not how Vesper theory works. So the second lone pair has to go opposite. Doesn't matter where you put the first one, but the second one has to go opposite, and we end up with square now plane. Because it's all in one plane. There we go. Okay, does that help a little bit with the, yeah? Okay, so if you want to come to my office and play with models, we can make all kinds of molecules, and I think that does generally help. I'm a particular person who is not, I do not have a highly developed skill of visualizing 3-dimensional molecules and manipulating them in my head. A lot of you guys do, but I don't. I struggle a little bit with that, so seeing them in 3D is really important for me. If you feel the same way, come on by. And don't forget, the dining hall is full of toothpicks and marshmallows and things like that, and they make really nice models as well. So gumdrops, the benefit is you can eat the gumdrops too as you're studying, you know, like you go from octahedral to square pyramidal by eating one of your electron groups, and that's not a bad deal either. So don't forget that. We'll do some molecules a week in a minute, but let's dive into chapter 8. Just getting 8 before we do that. Okay? Chapter 8 builds on everything that we've already learned, which is kind of nice. It's kind of nice when it's not disconnected. Yes, sir. Slide 60. I apologize. I want to move on. So listen up, guys. I will post the answer to that in the summary and announcements. If I forget, email me and I'll update it. Okay, because I also do not have a highly developed skill of remembering things. So let me know if I forget. Okay, so this chapter, we're going to delve a little bit into solids, really. And we're going to start by looking at phase diagrams. We're going to do a lab on this here in a couple of weeks. Phase diagrams. So what a phase diagram does is show temperature versus pressure. If you remember back to our, is that laptop in the very, very back could go away? I would appreciate it. Oh, two of them actually, I just saw there. If you remember back to chapter 5, when we talked about gas laws, right? We talked about ideal gas behavior, and that was related to the temperature and pressure conditions that we had, right? So it makes sense that if we change our temperature and pressure conditions, we're going to change the behavior of our substance, and in particular, we're going to change the phase. So if we look up here, what we see is that this happens to be for carbon, and you may not have realized that carbon has quite as many phases as it does. You're probably accustomed to thinking about graphite and diamond, right? You know that those are two what we call allotropes. You don't need to know that word, but that's the fancy word for the same element, just different phases of it. Diamond, graphite, so you can see this kind of explains why your pencil doesn't turn into a diamond in your pencil pouch in your dorm room, because you really need carbon to be at really high temperature, really high pressure, or high temperature, or both, to get the formation of the diamond. Okay, but you probably don't think about vapor-based carbon all that often. But we can manipulate the condition such that in theory we can get that. And we can also, in theory, manipulate our conditions such that we can have liquid carbon. And so there's two very broad classifications of solids called crystalline and amorphous. Okay, crystalline means pretty much exactly what it sounds like. We're talking about solids that exist in crystal lattices, so we have regular repeating structure. We're going to say that a little bit more specifically. We're going to say regular repeating geometric arrangements. And we'll explore those arrangements here in a minute. Amorphous solids solidify into random arrangements. And so we've got some depictions here of crystalline, so you can see the nice repeating units. You've got alternating, bigger, smaller, nice, neat, orderly pattern of arrangement. And amorphous, you can see there's no real repeating pattern there at all. It's kind of all over the place. Okay, it seems like these types of really related to band theory you're going to change, but I picked it because what's the shape? Trigonal, pyramidal, very good. So if you were to draw the Lewis structure, you would see that it has 4 bonding regions. What's the geometric name? Tetrahedral. It is tetrahedral, but one of the regions is a lone pair up there on the top. So imagine a lone pair on my head, and it pushes those bond angles down. And well, okay, I'm not good. Okay, so if this is tetrahedral, right? We just took one of the bonding pairs off, and now imagine, this is going to be funny to you all. Imagine tipping me over this way so that I'm doing some kind of funky yoga pose where both of my feet and my arm are all on the ground at the same time. We're not going to try that. That would go badly wrong. I'm too old for that. But that's the idea. Okay, nitrogen triiodide. Christopher Pitts is one of my former students. He suggested this video. So if you have molecule of the week suggestions, feel free to pass them along. Nitrogen triiodide is a really sensitive contact explosive. So what we're going to see in the video is it is so sensitive that you can make it explode by touching it with a feather. But you don't actually even have to touch it with a feather. Why would you want to do that?
Wile E. Coyote.
Oh, Wile E. Coyote does nitrogen triiodide?
No,
Oh, he would love it. You're right. That's a good point. Wile E. Coyote would like it. You could actually just breathe on it and make it explode. The reason it's so sensitive is due to the instability of the nitrogen triiodide. And nitrogen triiodide is so unstable because N2 is so rock solid stable. You're breathing a lot of N2 right now, so that's a good thing that it's not unstable, right? So N2 is really solid, stable. It's got that nice, let's see, 14, 2, 4, 6, 8. Is it a triple bond? It's a triple bond. A nice triple bond in N2, so it's good and solid and stable. So nitrogen triiodide really wants to go this way towards the N2 because that's a more stable configuration. You may have noticed a trend in chemistry. Nature likes to go towards stability and lower energy. So let's take a look at it. It's a pretty short video.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor.
They're kind of cool. It's kind of dangerous. You shouldn't play with it, but kind of cool, right? How they move it? That's a good question. I don't actually know how they move it without, I would suppose it's probably done, that was probably in some sort of fume hood or something like that, a box, something like that. Oh yeah, I'm sure they do. I'm sure they do, yeah. Yeah. Okay, I know that was cool, but back to focus.